Hello, welcome back to this series of videos where I am learning more about technical aspects of Bitcoin. Um, just to have a quick recap, I'm going through the material of learning at chaincode.com. Yeah, you can know more about them in their landing page for the learning aspect. And now I will just quickly resume my last video. I've been through these two chapters of the Bitcoin white paper. I started this series of videos by analyzing the abstract and the title especially. I have seen how the introduction uses the key concepts expressed in this half page and merges them with the current scenario in the online payments. Current scenario for the white paper publication date. So nowadays we have a slightly different situation. And then as I was mentioning in the last video, we've been through the chapter of transactions and timestamp server, which are two chapters that again are just making the point, the current situation, and pointing towards a direction. There are some aspects that are already being mentioned, some aspects which are characteristics of this system, this solution that is being proposed here. However, it's again something that is written more as an observation than, a proactive solution proposal, in the sense that it looks like the author is just looking at this current situation, the current landscape where he was working, and the solution emerged. He just says, look, the problem with the current solution is that the fate of the entire money system depends on the company running the mint, with every transaction having to go through them. Because he was saying that solutions implementing electronic signatures were already existing and working. However, they did not have a way to share the knowledge about a common ledger. Therefore, the authors declared that we need a way for the payee to know that the previous owners did not sign any earlier transactions. Therefore, to avoid the basic issue of double spending. So even if you have a system where you already implemented electronic signature, cryptographic signature, you still need a system which distributes informations. So the electronic signature is the mechanism that allows you to move pieces in a landscape which has to be notable and knowable by all the actors involved. And this is something that was still missing. Therefore, to accomplish this without a trusted party, transactions must be publicly announced, and we need a system for participants to agree on a single history of the order in which they were received. Therefore, here we have, in other terms, the author is saying that we need a way to share a common history, a single history, a way to agree on a series of events. A series of events which functions also as a series of transactions ordered in time, which therefore allows a payee to check that the funds that he is going to receive are not already spent. And it's important to remember always that this network electronic payment system is based not on accounting systems. Instead, it's more it's more similar to cash than to bank. Banks are some spaces associated with an identity in which we put some amount of assets. Instead, in this case, we do not have an identity associated with the token. We just have a series of tokens from which other tokens emerge as spendable. So from each transactions, we have some tokens which will be declared as already spent, and some new tokens will emerge as spendable. The new token will include information about the private key, which will be able to sign a new transactions which spends these new tokens. And this action is, this mechanism is based on electronic signatures, and the information about which tokens are still spendable are registered in this series of blocks of transactions. This series of blocks of transactions is time-stamped. We have this entity which in this third chapter is called the timestamp server, which in this chapter is being discussed only as a role. So it's we can observe that it's not called timestamp servers. It's called a timestamp server, just one. So it's discussed as a role, as a generic entity, which functions as label mechanism, which assigns a timestamp to each block of this chain of blocks of transactions. And this is necessary because of the clearance mechanism, distributed clearance mechanism, which is based on a time chain which can't be reordered in other ways than the only time chain that has emerged as the one that all the participants agree on as the real and the only existing chain. This chain emerges from a continuous battle between chains of nearly the same dimension, which are being elected by a mechanism which we'll see just after, maybe in the next. In this chapter I think we already see how at each moment, at each step in this time chain, in this chain of blocks of transactions, we continuously choose in which direction to expand the longest chain. Therefore, as it's already clear, today in this video I will discuss this chapter, the chapter about proof of work, and maybe the chapter about network. So the chapter about proof of work has 1, 2, 3, 4 paragraphs and an illustration, a little chart here. So let's have a look. Today I feel like to use this method of just reading before fastly what do we have in each paragraph, and then we start relating them. So in the first one, we have these statements. To implement a distributed timestamp server on a peer-to-peer basis, we will need to use a proof-of-work system similar to Adam Back's Hashcash, which is mentioned in the notes, rather than the newspaper or Usenet posts. Okay. So this first statement, it's interesting because, as I was underlying, here we are talking about a unique entity called a timestamp server, which is being discussed only from the from how this role has to be implemented, what are its functions, and it's mentioned that a timestamp server works by taking a hash of a block of items to be timestamped and widely publishing the hash, such as in a newspaper or Usenet post. So he's mentioning these notes here from 2.5. And to accomplish this without a trusted party, transactions must be publicly announced. Okay, so here we are talking about the publishing examples. Let's have a look what are these resources which they mention. So let's have a look if this still exists in the normal web. Otherwise, we can check this in an archive. Yeah. Wow, it's incredible. So I'm in love with this. It's just a plain text published on the internet. Oh my god, it's incredible. So written by Wide Eye, last modified 2021. Incredible. If you wish to encrypt your email to me, you can download my PGP public key here. Incredible website. I will just save this. It's not certified, who cares? So cryptography, anonymity, social cost of intelligence, miscellaneous ideas, decision theory, other places I used to hang out. Incredible resource. And in particular, it says B money. Do we have B money here? No. How do we arrive to the main website from here? Maybe it's not possible. Oh yeah, it's possible. So in anonymity, B money, a scheme for a group of untraceable digital pseudonyms to pay each other with money and to enforce contracts among themselves without outside help. Let's have a look. So this paper was published in we do not have a date. It was something like October or no, it was January 2009. Therefore, if I go to archive, internet, Wayback Machine, I'm just curious to see what was the state of this homepage in this. Okay, so in February, look here. So this in 2007. Oh shit, sorry. So let's have a look at previous. I'm curious when was published B Money. So yeah, we're studying basically a bit of history of these resources. I think we need to go before 2007. Let's see if we can go to 2006 already. Oh, okay. Oh, look here. So we're already in 2004, and these, let's have a look. This article was written like this, and it looks like similar. Yeah, it looks like the same. So this guy here is maintaining this TXT article since at least 2004. He's taking it slowly. Okay, so in 2000 there was already this article. My god. So this is something. This is something, guys. I'm really curious about the history of these emblematic pages. Okay, so we're already in 1998, and this article is still here. Okay, but look here, we have a different version, maybe? Yeah, it looks a bit different. Oh, this is an appendix that has been added like in 2000 and something. Okay, really interesting stuff. Let's have a look if, oh yeah, like in one year after, like in 2000, there was already a new capture here. So Wei Dai, I'm curious who's this guy, Wei Dai, computer scientist, Wei Dai. So Wei Dai is a computer engineer known for contribution to cryptography and cryptocurrencies. He developed the Crypto++ cryptographic library, created the B-Money cryptocurrency system, and co-proposed the VMAQ message authentication algorithm. So, Bachelor of Science degree from the University of Washington with a minor in mathematics. This guy here may be Satoshi. Him or maybe other people together with him. As an intensively private computer engineer, okay. In 1998, I helped to spark interest in cryptocurrencies. Okay. But is there something about him, like a person, like maybe the age? I'm curious. I just want to know. Oh, from the 76, 49 years old. Nice. Why die? So this guy here, let's see if he has some other publications. I was a research partner at Bain. I am not the author of Crypto++ or inventor of B-Money. Ah, okay, so this guy has the same name as, okay. So he's not the guy we're looking here. PipeNet, a protocol for anonymous communication. I will just continue to go back in time. I think that this is the oldest capture we have. So this is from 25 December, no, 25 November. Let's have a look if we have something earlier. Nice, interesting. Okay, so we have a historical context about this article here, which maybe we will go through just to have some ideas why this was mentioned here. So I'm fascinated by Tim May's crypto anarchy. Tim May's crypto anarchy. Timothy May, crypto anarchist manifesto. Wow. MIT. Okay, another cool website, which is plain text. Well, in this case it's HTML, but nearly plain text. A specter is haunting the modern world, a specter of crypto anarchy. Computer technology is on the verge of providing the ability for individuals and groups to communicate and interact with each other in a totally anonymous manner. Okay, well, we read just the first statement. The technology for this revolution, it surely will be both a social and economic revolution, has existed in theory for the past decade. The methods are based upon public key encryption, zero-knowledge interactive proof system, and various software protocols of interaction, authentication, and verification. The focus has until now been on academic conferences in Europe and US. Conferences monitored closely by the National Security Agency. But only recently have computer networks and personal computer attained sufficient speed to make the ideas practically realizable. And the next 10 years will bring enough additional speed to make the ideas economically feasible and essentially unstoppable. High-speed networks, ISDN, tamper-proof boxes, smart cards, satellites, Q-band transmitters, and so on, and encryption chips now under development will be some of the enabling technologies. The state will of course try to slow or halt the spread of this technology, citing national security concerns, use of the technology by drug dealers and tax evaders, and fears of societal disintegration. Many of these concerns will be valid. Crypto anarchy will allow national secrets to be traded freely and will allow illicit and stolen materials to be traded. An anonymous computerized market will even make possible abhorrent markets for assassination and extortion. Various criminal and foreign elements will be active users of CryptoNet, but this will not halt the spread of crypto anarchy. Just as the technology of printing altered and reduced the power of medieval guilds and social power structure, so too will cryptologic methods fundamentally alter the nature of corporations and government interfaces in economic transactions. Combined with emerging information markets, crypto anarchy will create a liquid market for any and all material which can be put into words and pictures. And just as seemingly minor inventions like barbed wire made possible the fencing of vast ranches and farms, thus altering forever the concepts of land and property rights in the frontier West, so too will the seemingly minor discovery out of an arcane branch of mathematics come to be the wire clippers which dismantle the barbed wire around intellectual property. Arise, you have nothing to lose but your barbed wire fences. Wow, this is powerful. Yeah, so sorry, I was reading these and I could not show you entirely. I didn't pay attention. Okay, nice words, powerful words, which are being mentioned here. unlike the communities traditionally associated with the word anarchy, in a crypto anarchy, the government is not temporarily destroyed but permanently forbidden and permanently unnecessary. It's a community where the threat of violence is important because violence is not possible, and violence is impossible because its participants cannot be linked to their true names or physical locations. Until now, it's not clear, even theoretically, how such a community could operate. A community is defined by the cooperation of its participants, and efficient cooperation requires a medium of exchange, money normally, and a way to enforce contracts. Traditionally, these services have been provided by the government or government-sponsored institutions and only to legal entities. In this article, I describe a protocol by which these services can be provided to and by untraceable entities. To and by untraceable entities. I will actually describe two protocols. The first one is impractical because it makes heavy use of a synchronous and unjammable anonymous broadcast channel. However, it will motivate the second, more practical protocol. In both cases, I will assume the existence of an untraceable network where senders and receivers are identified only by digital pseudonyms, public keys, and every message is signed by its sender and encrypted to its receiver. In the first protocol, every participant maintains a separate database of how much money belongs to each pseudonym. Okay. These accounts collectively define the ownership of money, and how these accounts are updated is the subject of this protocol. The creation of money. Anyone can create money by broadcasting the solution to a previously unsolved computational problem. The only conditions are that it must be easy to determine how much computing effort it took to solve the problem, and the solution must otherwise have no value, either practical or intellectual. The number of monetary units created is equal to the cost of the computing effort in terms of a standard basket of commodities. For example, if a problem takes 100 hours to solve on the computer that solves it most economically, and it takes 3 standard baskets to purchase 100 hours of computing time on that computer on the open market, upon broadcast of the solution to that problem, everyone credits to the broadcaster account by 3 units. Okay, this is so interesting because it's actually discussing about the connection between the computing effort and the value of this effort in basket of commodities. And here in this paragraph, we can already see a lot of concepts which are characteristics of the Bitcoin network, like the adjustment of the computing effort, the evolution of the machines which are used to solve the computational problem. And it's interesting how this is being linked to a basket of commodities. Okay, so there's some computation problem to be solved. Then the broadcasting of transaction between accounts. So this system is based on accounts. The effecting of contracts. A valid contract must include a maximum reparation in case of default for each participant party to it. It should also include a party who will perform arbitration should there be a dispute. All parties to a contract, including the arbitrator, must broadcast their signature of it before it becomes effective. Upon the broadcast of the contract and all signatures, every participant debits the account of each party by the amount of his maximum reparation and credits, blah blah blah. So this is more about escrow systems, multi-sig escrow, blah blah blah. Okay, so key A agrees to send key B the solution to problem P before this. Okay, so key B agrees to pay KA 100 monetary units before. In case of disputes, K agrees to pay a maximum of in case of default, blah blah blah. So this is already defining the problems in forms of scriptable conditions. The conclusion of contracts. If a contract concludes without dispute, each party broadcasts a signed message. The contract with SHA-1 concludes without reparation, blah blah blah. Or possibly the contract with this hash concludes with the following reparations. Therefore, upon the broadcast of all signature, every participant credits the account of each party by the amount of his maximum reparation, removes the contract account. Okay, so each contract also has an account. The credits or debits the account of each party, blah blah blah. The enforcement of contracts, so it continues defining basically ideas on how this first protocol needs to the concepts that are needed to be managed and how they can be managed. In the second protocol, the accounts of who has how much money are kept by a subset of the participants, called servers from now on, instead of everyone. These servers are linked by a Usenet style broadcast channel. So here we have the passage that Weidai was mentioning, saying, okay, I present you a first protocol which will be impractical, because everybody will need to basically maintain a database, and it will be updated by broadcast message sent and received. Therefore, everybody needs to put this effort to keep everything up to date with the network. In the second protocol, instead of everybody, the accounts of who has how much money are kept by a subset of the participants, and these subsets are called servers, and they are linked by a Usenet style broadcast channel. The format of transaction messages broadcasted on this channel remain the same as in the first protocol, but the affected participants of each transaction should verify that the message has been received and successfully processed by a randomly selected subset of the servers. So here it's more like a jury which is being formed every time, and they need to serve the network as jurors. Since the servers must be trusted to a degree, some mechanism is needed to keep them honest. Each server is required to deposit a certain amount of money in a special account to be used as potential fines or rewards for proof of misconduct. Also, each server must periodically publish and commit to its current money creation and money ownership database. Each participant should verify that his own account balances are correct and that the sum of the account balances is not greater than the total amount of money created. This prevents the server, even in total collusion, from permanently and effortlessly expanding the money supply. So this statement is saying that to cheat, you need to collude and to pay a high cost, but it's still possible to expand the money supply in your favor. New servers can also use the published database to synchronize with existing servers. Okay, so here we have a peer-to-peer style where you can join and get out. The protocol proposed in this article allows untraceable pseudonymous entities to cooperate with each other more efficiently by providing them with a medium of exchange and a method of enforcing contracts. The protocol can probably be made more efficient and secure, but I hope this is a step toward making crypto anarchy a practical as well as theoretical possibility. Then this first part was written in 1998. Then in 2000, Appendix A was added, right? Yeah. Alternative B-money creation. One of the more problematic parts in the B-money protocol is money creation. This part of the protocol requires that all of the account keepers decide and agree on the cost of particular computations. Unfortunately, because computing technology tends to advance rapidly and not always publicly, this information may be unavailable, inaccurate, or outdated, all of which will cause serious problems for the protocol. This protocol will be like, imagine an economy which works fine, but then an alien economy comes in contact, an alien economy with higher technology. This happened, for example, when Europeans arrived in South America, and Europeans as an alien economy were technologically more advanced, and they took advantage of the economical mechanism of the South Americans, in the sense that their money generation mechanism was easily forgeable by European technology at that time. Therefore, it happened that Europeans took over this economy, and this will be the same expressed here, as we in that time it wasn't possible to evaluate exactly the real cost in real economy terms, the cost of a computing problem. It wasn't possible to decide the right computing difficulty, because if someone secretly had a really huge advancement in computational techniques, they could leverage that secret in order to resolve easily with a high degree of economical advantage respect to others, some computing issues that were published and decided without knowing the advancement of that secret part. Therefore, the creation of money in this case will be exploited by more technologically advanced part of the society. So I propose an alternative money creation subprotocol in which account keepers, everyone in the first protocol or the servers in the second protocol, instead decide and agree on the amount of B-money to be created each period, with the cost of creating that money determined by an auction. Each money creation period is divided up into 4 phases as follows. Planning. The account keepers compute and negotiate with each other to determine on optimal increase in the money supply for the next period. Whether or not the account keepers can reach a consensus, they each broadcast their money creation quota and any macroeconomic calculation done to support the figures. this is complex. I don't really understand how this can be implemented. Maybe this is how central banks work. I'm not sure. And then we have a bidding, which is the second phase, where anyone who wants to create B-money broadcasts a bid in the form of XY, where X is the amount of B-money he wants to create, and Y is an unsolved problem for a predetermined problem class. Each problem in this class should have a nominal cost, which is publicly agreed on. Then computation. After seeing the bids, the one who placed bids in the bidding phase may not solve the problems in the bids and broadcast the solution. So you solve your own problem, okay? Money creation. Each account keeper accepts the highest bids among those who actually broadcast the solution in terms of nominal cost per unit of B-money created and credits, and the bidders account accordingly. So we have account systems here, which is different from the token system implemented in Bitcoin. And these accounts are not using a real proof of work. They are using something that is a mix between proof of work and proof of stake, as the servers, which in the second example of the protocol need to be kept honest, they will provide a grant, something which will be a cost for them in case they do not behave honestly. But then it remains another problem, which is to decide the difficulty of the associated computational problem, which allows money creation. To agree on this difficulty, we have this four-phase sub-protocol, which is still it's still open to some misconduct, in the sense that in the planning and bidding, one can declare a difficulty, an unsolved problem, which can be already resolved secretly by them and with a lower cost than one declared and agreed by the entire network. This creates an asymmetry in the capacity of resolving computational problems and therefore the money creation. Okay, then, yeah, this part here, it looks really similar to the Bitcoin network. Like, yeah, there are characteristics of this sub-protocol, but they have similar ideas. Okay, so we can see that in 1998, 10 years before, the ideas were really similar. They were just trying to find a good way to orchestrate all these issues, the issue of authenticating and verificating transactions. So the authentication was already kind of achieved because electronic signatures were already something solid at that time. Hashing was already present here, as they were resolving computational problems, which I imagine, I'm not sure if they were hashes to be solved, but maybe they were just linear algebraic problems. The hashes were used to identify and authenticate. I'm not sure if they were used also as problems. However, we can see that there existed this proto this prehistoric version of the system that then has been described here, of course using this reference to it. And the argument of today from this paper is proof of work, which uses the idea of the timestamp server and the transactions done with electronic keys. And it's also interesting to go and see just a few seconds this other reference to Usenet posts, because also Waidai was referencing these Usenet posts, which I imagine that describe how the messages are distributed in these broadcast channels. So this first reference here is design of a secure timestamping service with minimal trust requirements. Okay, let's go. I will look for it like this. Satoshi Nakamoto Institute. Okay, what do we have? Like, let's see if we have a DOI for this article. So this is University of Leuven. Wow, who's this guy? Okay, so let's have a look at the paper. Just a second. I need to put on this. Okay, design of a secure timestamping service with minimal trust requirements. Okay, so this paper was published by these people here at Leuven in Belgium, the Leuven University. And it presents a design of a timestamping system for the Belgium project TimeSec. We first introduced the timestamping method used and we justify our choice for it. Then we present the design for our implementation as well as some of the important issues we found and the solution we gave to them. The creation date of digital documents and the times expressed in them are becoming increasingly important, blah, blah, blah. Introduction of the timestamping techniques. There are two families of timestamping techniques. Those that work with a trusted third party and those that are based on the concept of distributed trust. Techniques based on a trusted third party rely on the impartiality of the entity that is in charge of issuing the timestamps. Techniques based on the distributed trust consist of making documents dated and signed by a large set of people in order to convince the verifiers that we could not have corrupted all of them. The trusted third-party techniques can also be classified into two different kinds. Those where the third party is completely trusted and those where it is partially trusted. A detailed study of timestamping techniques can be found in MQ97. Okay. We believe that techniques based on distributed trusts are not really workable in a professional environment. That is why we concentrate on the trusted third-party approach. Nevertheless, we impose to ourselves the requirement to lower the necessary trust on the third party to the maximum extent. So the easy solution, which consists on concatenating the document with the current time and assign the result, has been discarded because it has two main drawbacks. We must completely trust the third party. The limited lifetime of cryptographic signatures, which can be shorter than the document time to life. The limited lifetime of cryptographic signatures, which can be shorter than the document time to life. Okay. The timestamping method that we have chosen uses a binary tree structure and has been described in this. Okay. This method works by rounds. For each round, a binary tree is constructed with the request field during it. Each of the timestamp requests consists on a hash value of a given document. The leaf of the tree are each of those hash values. The leaf values are then concatenated by 2 and hashed again to obtain the parent value. The process is separated for each level until a single value is obtained. Finally, the top value of the round tree, called the round root value, is then concatenated with the value obtained for the preceding round and then hashed again to obtain the actual round value. Okay, so it's a series of concatenation which allows a unique combination of timestamps. Okay, a very useful method for extending lifetime is described. It consists on real-time stamping the hash of the document. Okay. Description and analysis of the timestamping implementation. Okay, we will now introduce the basic design of the system we have developed, which is based on the technique introduced above. Initially, the user designates a document to be timestamped. 2 hashes of it are created using a SHA-1 and RIP-MED 160 algorithms. The request containing the 2 hashes is then sent by the client to the STA. Upon the request received, the STA creates the corresponding timestamp using the following process. Okay, so here we have a third party Okay, so we have a server basically doing the timestamps. Okay, so this is really practical, and they basically build a Merkle root. I'm not sure if this is a Merkle root, but yeah, it looks like something similar to what we have today in Bitcoin. How to timestamp a digital document. So here basically we are looking at all these articles which are basically studying all the issues that come when you need such a technique, when you need to implement these techniques. Let's see, fit to page. No. How do I print? No. Okay, we'll download it. And now we can open it. Okay. So this is another article in which the prospect of a world in which all text, audio, picture, and video documents are in digital form on easily modifiable media raises the issue of how to certify when a document was created or last changed. The problem is to timestamp the date and not the medium. We propose computational practical procedures for digital timestamping for such documents so that it's infeasible for a user either to backdate or forward date his document, even with the collusion of a timestamping service. Our procedures maintain complete privacy of the documents themselves and require no record keeping by the timestamping service. So in many situations, okay, so here's been discussed again how to trust timestamping services. The purpose of this paper is to introduce a mathematically sound and computationally practical solution to the timestamping problem. In the section that follow, we first consider a naive solution to the problem, the digital safety deposit box. This serves the pedagogical purpose of highlighting additional difficulties associated with digital timestamping beyond those found in conventional methods of timestamping. Successive improvements to this naive solution finally lead to practical ways to implement digital timestamping. So the setting, okay, a naive solution, a digital safe box. So however, this approach raises several concerns. Privacy, in two ways, a third party could eavesdrop while the document is being transmitted. Okay, so a trusted timestamping service. Hash. Our first simplification is to make use of a family of cryptographically secure collision-free hash functions. Okay. So for the rest of this paper, we speak of timestamping hash values, random appearing bit strings of a fixed length. Part of the procedure for validating a timestamp will be to produce the pre-image document that satisfies the hash function. Inability to produce such an X invalidates the putative timestamp. What we have described so far, we believe a practical method for timestamping digital documents on arbitrary length. However, neither the signature nor the use of hash functions in any way prevents the timestamping service from issuing a false timestamp. Ideally, we would like a mechanism which guarantees that no matter how unscrupulous the TSS is, the times it certifies will always be correct ones, and that it will be unable to issue incorrect timestamps even if it tries to. So here we have the word linking. Our first solution begins by observing that the sequence of clients requesting timestamp and the hashes they submit cannot be known in advance. So if we include bits from the previous sequence of clients requests in the signed certificate, then we know that the timestamp occurred after these requests. But the requirement of including bits of previous documents in the certificate can also be used to solve the problem of constraining time in another direction. Because the timestamp company cannot issue later certificates unless it has the current request in hand. So I will not continue this paper because at this point we have, okay, so this is another interesting chapter. For this scheme, we assume that there is a secure signature scheme so that each user can sign messages and that a standard secure pseudo-random generator G is available to all users. A pseudo-random generator is an algorithm that stretches short input seeds to output sequences that are indistinguishable by any feasible algorithm that from a random sequences in particular they are unpredictable. Okay, so here we have things like finite fields and elliptic curves mathematics, which function as functions which are which do not have predictable times to reverse them. In many cases, this time is a gigantic time. I'm not sure if it's about this type of mathematical function that they're talking here, but the idea is that you make it so hard to reverse a mathematical function. Therefore, when you get a pseudo-random generator G, which allows you to generate each point of these curves that you are using, it's basically requires you to iterate point by point without the possibility to understand which is the function, the graphical function. So you don't know the general trend of this curve, therefore you cannot discover the points on the curve by just knowing a generator. Having the generator allows you only to explore the curve point by point, and this will take you forever, therefore you cannot reverse the function. Therefore, using such type of mathematical functions enforces the use of double hash to create a link of hashes, which is really costly to be forged. So distributed trust. For this scheme, blah blah blah. This scheme need to use a centralized SSL to not use. The only requirements are that it's possible to call up other clients that will and receive from them the required signatures, and there be a public directory of clients so that it is possible to interpret the output of G in a standard way. Okay, so here it's already talking about a network basically. If you want to eliminate a third party, you need a network which at each time allows you to ask random nodes some pieces of information that allow you to check the status of the link of hashes. Okay, so this is a really interesting article here that was mentioned. Improving the efficiency and reliability of digital timestamping, secure names for bit strings, hash, a denial of service countermeasure. So, okay, let's see this article from Adam Beck, which looks like really interesting. Okay, so this is already in 2002. And it's an article by Adam Beck. Adam Beck, if I'm not wrong, he's still living. He's 54. And he's cool. Okay, so Hashcash was originally posted as a mechanism to throttle systemic abuse of unmetered internet resources such as email and anonymous remailers 5 years on, this paper captures in one place the various applications, improvements suggested, and related subsequent publications, and describes initial experience from experiments using Hashcash. So yeah, I've heard about this, where you have a network of email servers and clients. You may want to reduce spam, so each action, if you introduce a cost, an incremental cost for each action, everybody will keep a lower profile and will not be easy to abuse and to spam. And it looks like this Hashcash was something used in that context. The Hashcash CPU cost function computes a token which can be used as a proof of work. Interactive and non-interactive variants of cost functions can be constructed with which can be used in situations where the server can issue a challenge. Okay. So to take part to a network, you will need to resolve a riddle, and this introduces a cost. Therefore, you will decide to continue participating in the network because the value you're gonna receive by participating to the network honestly will not necessarily honestly, but your behavior will be conditioned by the cost you already put in the network. So introduction, Hashcash was originally proposed as a mechanism, blah, blah, blah. Time of publication, the author was not aware of the prior work by Dwork and Nauer, who proposed a CPU pricing function for the application of combating junk email. Subsequently, applications for cost function have been further discussed by these people, and Jacobson and Jules proposed a dual purpose for the work spent in a cost function. So here we have the part of introducing a cost in the actions you perform in a digital world. So this was not intended as a money, as a cash system. This was intended as a regulator, a system that regulates behavior in a network. There was a mint function, cost function mint, which is used to create tokens to participate in a protocol with a server. Therefore, the server was distributing tokens not to agents that were going to spend these tokens with other agents. The agents, the clients, were going to use these tokens to basically demonstrate their honesty and their good behavior, their commitment to a good behavior with the server itself. The server will check the value of the token using an evaluation function value and only proceed with the protocol if the token has the required value. So when you emit a token to someone, you can create a shadow token or something which allows you to check if that token is really a good one. The functions are parameterized by the amount of work that the user will have to expend on average to mint a token. Okay. With interactive cost functions, the server issues a challenge sheet to a client, to the server use the whole function to complete the challenge. So the work that the agent will need to perform changes in difficulty, I imagine based on the channel saturation maybe, or something like this. So publicly auditable probabilistic cost. Publicly auditable cost function can be efficiently verified by any third party without access to any trapdoor or secret information. Fixed cost, probabilistic cost. Okay, so here are being introduced concept and issues like the possibility to publicly check the transactions and the token and the minting and all these mechanisms which are part of a network where each agent may have the role as client or auditor. So I'm not deeping into this for now. Maybe I will get back to it as it looks really well done. Wow, it's really something, this. I mean, it's really incredible work. What is Usenet? Is something like Telnet? Users Network is a worldwide distributed discussion system available on computers. It was developed from the general purpose idea. Usenet resembles a bulletin board system in many respects and is precursor of the internet forums that have become widely used. Okay, so discussions are threaded as with web forums. Though posts are stored on servers sequentially. Okay, so it was a network of messages. Usenet. Okay. Cost function classification scheme. So this paper is concluded with some open problems. The existence of efficiently verifiable non-interactive fixed cost functions. Existence of efficiently verifiable non-interactive non-parallelizable cost function. So here the open problems look like about the evaluation, of cost functions with these characteristics: efficiently verifiable, non-interactive, fixed cost. So they were basically checking the existence of this type of functions. Okay, so this was already a problem that was published and left for the future studies. Look here, Halfine. Okay. Therefore, having all these context, this guy here in 2009 decides that transactions which are based on electronic keys, which use the idea of a timestamp server and which needs obviously a distributed timestamp server, will need to use a proof of work system similar to Adam's back hash cache. Therefore, the distributed timestamp server will perform the linking of each block using this behavior regulation based on hashing, which introduce a cost to each action. Okay, instead of using these techniques. So it's stating that proof of work is necessary. The proof of work involves scanning for a value that, when hashed, the hash begins with a number of 0 bits, a certain number of 0 bits. So it's already saying that the average work required is exponential in the number of 0 bits required and can be verified by executing a single hash. So the verification, once the solution is published, is executable in a single hash, a single operation, hash operation. Instead, the work required to resolve this problem before knowing the solution requires an exponential number of like the computational work is exponential respect to the number of zeros I want the hash to begin with, because when calculating a hash I will receive a random value as an output, and this value may start with some zeros. So in order to achieve the number of zeros pre-declared as challenge, I will need to introduce some changes. Basically, the part that is being changed, I think, is called nuance. So if I'm calculating the hash of something, I change this something until I receive the numbers of zeros I have been challenged to obtain. This is, I will say, a bad way to express of these 4 sentences, 3 or 4 sentences. So the first paragraph is saying we will use proof of work, and the proof of work will be a behavior regulator in a peer-to-peer timestamping network. The timestamping will be nudged to be honest because we will introduce a cost to each linking action. This action will be verifiable easily and will have a huge cost to be executed. The huge cost part, maybe it's not really good to say it like this, because as we've seen in Adam's back hashcash, it's not just a huge cost, it's the right cost for that network for that moment. So for our timestamp network, we implement the proof of work by incrementing a nonce, I was saying nonce before, a nonce in the block until a value is found that gives the block hash the required 0 bits. So this part here is equivalent to say that you have a finite field on which you project an elliptic curve, and given just one point of this elliptic curve, you have to discover the others, basically. And in order to discover the other points, you cannot just use the information about the curve, because the curve can be anything. You don't know the shape of this curve. So to discover the points until you arrive to the point that you need, then in that case you need to iterate a huge number of times, a huge number of hash, until you find the right point. Here I may be kind of imprecise when doing the analogy between this statement and the elliptic curves mathematics statement. However, I feel that I'm quite close to expressing it well. Once the CPU effort has been expended to make it satisfy the proof of work, the block cannot be changed without redoing the work. As later blocks are chained after it, the work to change the block would include redoing all the blocks after it. Therefore, if you want to change a transaction A, you then have to change and recalculate all these transactions after. And this implies a huge work, a huge cost. The proof of work also solves the problem of determining representation in majority decision making. So here in these first two paragraphs, the proof of work based on hash is introduced as a way to create a link of blocks. And this paragraph starts by saying you do not only create a link of blocks ordered by time and which are hardly costly changeable, you also are obtaining an output which implies which was the majority decision making. What was the majority deciding? If the majority were based on one IP address, one vote, it could be subverted by anyone able to allocate many IPs. Proof of work is essentially one CPU, one vote. The majority decision is represented by the longest chain, which has the greatest proof of work effort invested in it. Okay, so here it's saying that we are in a system where the votes are brought by the computational power. The computational power has a cost, and the majority decision is represented by the longest chain, so the chain that intrinsically has the most work in it, which has the greatest proof of work effort invested in it. This is a better way to to say the greatest proof of work effort invested in it. If a majority of CPU power is controlled by honest nodes, the honest chain will grow the fastest and outpace any competing chains. Okay, so it's important to remember that always that we have continuously competing chains. And it's not just competition about honest behaviors and not honest behaviors. It's just that the world is happening in many points at the same time, and CPU power is distributed in an asymmetric way all among this world. Therefore, where the CPU power is concentrated, there we have the pool of CPU power which will determine which is the next step in the link of blocks. To modify a past block, an attacker would have to redo the proof of work of the block and all the blocks after it, and then catch up with and surpass the work of the honest nodes. So if you want to rewrite the history, the links of blocks, you need to go to the point in time you want to modify and go and basically redo all the history while the history is continuing. Therefore, you do not only need to be more powerful than another, you do not only need to have more computational power than the biggest, the already biggest pool of computational power. You need to dedicate some of your power also to modify the past while the present is continuing to evolve. Therefore, the amount of the cost to perform this action is a challenging one. It's challenging to acquire such a power. We will show later that the probability of a slower attacker catching up diminishes exponentially as subsequent blocks are added. So this is an important corollary which says that considering everything that was said, the security of a block not being changeable augments with time. So the more blocks are added on top of the block you just transacted, the block where your transaction is in, the more secure your transaction begins, because it's like it augments the computational power needed to change your transaction, the block where your transaction is. To compensate for increasing hardware speed and varying interest in running nodes over time, the proof of work difficulty is determined by a moving average targeting an average number of blocks per hour. So these, I'm not sure if it's the answer to the open problems left at the end of Adam's back Hashcash paper, but here it's saying that there's a way to calculate the right difficulty so the number of blocks per hour will stay constant. So each 10 minutes we have a new block, and each block has its difficulty. So if at the end of a time window, we produce too much blocks, we will rise the difficulty. So in the next time window, we will probably, with the same hash power of the network, we will go down. And if the number of blocks was too low respect to our expectations, we will lower down the difficulty, and so on. So the difficulty will be determined by a moving average, time moving average of the of the resulting blocks per hour. Therefore, we discussed this proof of work chapter using also the informations from these two chapters. I will say that these 2, 3, and 4 chapters are really, I will say, they coexist. It's impossible to separate them because these two chapters are building the base for this one. And it's so interesting to go and have a look at the papers that are being cited, as they show not only the historical and intellectual context in which this paper is based, it shows the intellectual effort to participate in this discussion. So the paper, as we already said, is written in a really clear, minimal, and functional, and really valuable way. And it's evident that the person or the persons which wrote this paper have been through decades of techniques, of protocols that were imperfect and that needed some changes, and in the end they obtained these ideas, starting from decades of work of mathematicians which were thinking and writing articles, thinking about protocols, implementing, giving results, posing new problems. And by knowing all of these details, all of this effort going on, it it looks like this paper, this chapter, emerged as the necessity which is clear at the eyes of who's watching that landscape, that environment. So it's really interesting to read this paper, going through what was happening around at that time. It makes clear why this is not only a smart paper, a smart protocol, a smart system, smart, I would say more clever solution, but it's also a natural solution, I would say. It's a natural solution that is proposable by someone which was dedicating time to studying these issues, to studying the results of other people dedicating time to this. So it's kind of a chain of knowledge. It's a chain of efforts dedicated to a greater, to some. No, I was going to say to a greater result, but in reality, I was thinking to all these people that in reality was proposing solution to sometimes little problems, and then expanding these techniques to broader contexts. So yeah, I'm fascinated about all of this, and I'm really happy to study it. I hope that my effort in transmitting and rewarding all this concept achieved a good level of clarity, a good level of understandability. I hope it's not. Of course, I will need to improve, but yeah, I put an effort in making things clear and while elaborating them again. So maybe next time I will restart by rereading these 4 paragraphs, which in the first part are talking about how to influence the behavior of some agents in a network by using hash functions with a certain cost, and how by using this proof of work based on hashing you obtain also a solution to the problem of determining representation and majority decision making, the Byzantine kings issue, the problem of the Byzantine kings coordinating themselves. So thank you very much. I hope you enjoyed this, and see you